Hello everyone, my name is Goncalves and today I'm going to be presenting our work on jointly learning from unimodal and multimodal rated labels in audiovisual emotion recognition. Audiovisual emotion recognition plays a critical role in several applications across human-computer interaction systems, with applications in healthcare, entertainment, education, and more. Currently, most traditional methods with audiovisual emotion recognition are focused around learning from single labels and with unimodal stimuli in multimodal settings. The setup limits the capabilities of systems being able to perform in more complex scenarios, and it is important to not overlook that human emotion perception varies with different modalities, audio only, visual only, or audio visual. So our work works on addressing this gap by integrating annotation from multiple modalities. In this study, we explore two main questions. First, can combining annotations from audio only, visual only, and audiovisual stimuli enhance the performance of the audiovisual emotion recognition systems? And also, can integration of diverse annotation levels enhance the model's performance and calibration? So, in order to work on this problem, we formulate the multimodal emotion recognition and learning in the following way. So, traditionally, we have annotators give many annotators give annotations to a single sample, and what happens a lot of times is that we take majority voting. So, like in a case like this, where the most of the annotations were neutral, the label would just the sample would just be labeled as neutral. However, here we want to be able to consider the distribution of these labels and not just disregard. As in previous works have shown, minority views matter, and it's important to take into account all the subjective evaluations by different annotators. So we would consider distribution over all the annotators, and then this sample such as this one could have an annotation of including neutrality and anger, also a little bit of sadness in the sample. So we're able to consider all the emotions and all the variations that is present in a subjective annotation setup. In order to conduct the study, we need a data set that considers and has many annotations across different annotators, and also includes annotations across different stimuli, because we're also exploring if the stimuli from only showing the annotators the audio only, or only the video, or the audiovisual affects that, and how we can leverage that within our models. So to do that, this study employs the CREMA-D corpus, which is used to train and evaluate the proposed strategy. So CREMA-D is an audiovisual data set featuring high-quality recordings from 91 actors of diverse racial and ethnic backgrounds, and it contains many sentences performing many emotional intents. And the dataset contains about 7,440 clips, and each are evaluated by an average of 7 raters, totaling 5 hours of data. And it also spans a wide range of classes across anger, happiness, sadness, fear, disgust, and neutral. Those are the choices that the annotators can pick. And in this work, we're not limiting to the classical 4 emotions, so we explore all the emotional ranges available. So the CREMA-D has a unique labeling strategy that involves perceptual evaluations under 3 conditions: audio only, video only, and audio visual. So this makes the data set particularly suited for our study, because it contains these types of different stimuli to the annotators. And in addition to that, the data set contains a lot of demographic details about the subjects across gender and also their racial demographics. So we can do an analysis covering all these different aspects, so we can check the fairness evaluation on trained audiovisual emotion recognition systems, which is often ignored in a lot of works. And then we set up the usage of this data set in speaker independent data splits, so we don't have any data leakage across different speakers. Now that we understand our study, data set, and setup, let's discuss our proposed methodology. We're using a two-stage training setup. So here's stage one. In stage one, we are training unimodal layers separately for visual and acoustic inputs. So we use the visual-only stimuli annotations for the visual layers and the acoustic-only stimuli for the acoustic layers. Additionally, we train copies of these networks using audiovisual stimuli. So these layers handle audiovisual stimuli separately within the visual and the acoustic parts of the model. Then once stage one is trained, we move then to stage two, which then we take these layers that we have first trained in stage one, and then we freeze them so we can pass them forward into our shared layers that it's going to process multimodal information. So these layers will process both audio and visual embeddings from the lower backbone layers. The audiovisual inputs are passed through a set of shared layers, followed by attentive statistics pooling to flatten the features. We then concatenate the extracted features, and which then we process them forward into a simple two-layer network at the top of the network. So this audiovisual predictor makes the final predictions using audiovisual stimuli labels. So in order to evaluate this model, we assess not only the results of the performance on multimodal setting using macro F1 score and weighted F1 scores, but also we do assess the model reliability. So we measure the calibration using the Breer score, which quantifies the accuracy of the predicted emotion probabilities. So here a lower Breer score indicates a better calibration, meaning that the model's confidence scores closely match the actual outcomes across different emotions. So we can see here the Breer score takes into account C, which is the number of an emotional classes, and where E denotes an emotion, and then N is the sample count for the emotions, P is the predicted probability for each specific emotion, and T is the ground truth. To evaluate and contrast these models with different approaches, first we have a set of baselines that we used that we built to have a similar structure to our model. The first type of baseline is an audio only, so this is an acoustic only baseline framework that basically has the same structure as just the acoustic part of the backbone. And then we also have a visual only framework that just takes the visual inputs and do emotion prediction. And then we also have a full framework that is similar to what we used in our final proposed method that contains the backbones, acoustic and visual networks, and also the shared layers. And we have two formulations. First is this formulation with single networks for each modality, and also we have the double networks for each modality that is the same as the proposed work. We just have a different mix of different stimuli in there that we're going to be talking about more in the results section. In addition to that, we do some analysis across some strong recent state-of-the-art audiovisual motion recognition baselines. Now let's dive into the results. So let's first break down the different model configurations. So indices 1, 2, and 3 are basically corresponding to the audio-only baseline that we built. And then we also train it with different elicitations of annotations at voice only, face only, and audiovisual annotations. Then we have indices 4, 5, and 6, which is the video only baseline, and similarly they have the different elicitations as well. And then indices 7, 8, and 9 correspond to the audiovisual model that we presented, and then we also train it with the different stimuli. Then when we get to indices 10, 11, and 12, this uses our proposed two-stage network. So 10 is training the first lower part of the network with just audiovisual stimuli, and then we include the second part training of audiovisual stimuli. 11 is using basically the same overall framework, but the audio only part is trained with the audio only stimuli and annotations without making the copy of it to train with audiovisual stimuli. And then the visual only is also only trained with the visual only stimuli with no copies for training audiovisual stimuli on the backbone. And then finally 12 is our final proposed network. So this setups allows for direct comparisons between different training approaches and input modalities. So looking at the results here, we can see that both acoustic and visual inputs lead to better performances than those with unimodal inputs, achieving a relative improvement of 8.05 and 15.95 compared to the acoustic and visual input models. So, and also notably, we see that the performances of the models indexed at 11 and 12, which integrate the mixture of the pre-trained models trained with the different perceptual evaluation elicited by varying modalities, it suppresses, it's better than the model solely focused on audiovisual labels, which would be maybe the closest model, the model 10. So these findings indicate that the perceptual evaluations elicited by different stimuli modalities contain supplementary emotional cues, augmenting the effectiveness of the audiovisual motion recognition system. Now, let's take a look at the model calibration and macro F1 scores per emotion. So we can see the models 1 through 9 showed improved performance with audiovisual labels, and our proposed method 12 achieved the best calibration and it's achieved better performance in recognizing fear. Models 11 and 12, which both utilize our proposed approach of combining unimodal and multimodally rated labels for training, outperformed others in anger and sadness recognition, highlighting the effectiveness of using this two-stage approach with perceptual evaluations across diverse stimuli. And also, please check out our paper for further results where we present additional results and analysis across different setups where we're exploring gender and demographics. And in this table here now, we summarize how our proposed method compares against state-of-the-art audiovisual emotion recognition models. As highlighted, our approach achieves the highest performance with a macro F1 score of 0.772 and a weighted F1 score of 0.767, which clearly outperforms the existing baselines with significance, statistically significantly, indicating that jointly incorporating audio and visual annotations effectively captures the emotional nuances, leading to superior recognition accuracy. In conclusion, we introduced a novel two-stage training approach that incorporates labels from audio only, visual only, and audiovisual annotations to better reflect human emotion perception, and our method significantly improved emotion recognition accuracy, outperforming state-of-the-art methods in macro and weighted F1 score and enhanced model calibration. Importantly, our method successfully reduced some biases as well that we showed on the paper, and moving forward we plan to expand the work on bias mitigation strategies and continue enhancing fairness across demographic groups. Thank you for your attention and your time. Feel free to leave any questions.